So let's start our first class. Okay, so today is the first day of our class. So thermodynamics. One second. Hello, hello. Okay. Hmm. So for this course, first what we will try to do? First we will try to solve the previous year assignment. Okay, so in our each class, so related to that class, first we'll discuss the assignments that have been done in previous year, and if time permits, then we'll also try to solve some different problems similar to that day's topic. Okay, so Ach- hmm. so that we basically do for this course. Okay, so let's start from the first problem. Okay, so so this is the problem one. Okay, uh, problem one. Problem one. The problem one is when 2 kilojoule of energy is added to a 10 liter of an ideal gas, the gas expands to 15 liter at a constant pressure of 1 atm. Now the problem is you have to calculate the change in internal energy. Okay, so this is our first problem. Okay, now so in the problem, so what are the information that are given in the problem? It's given that the energy that is added to the gas, so that means the heat energy mainly. Energy here by means energy, they are like referring the heat energy. So here dq is 2 kilojoule. As this is added into the system, so we are only taking like the positive value of it, and so this is it. So now, so we have to calculate the change in internal energy. So initial volume V1 is given 10 liter of an initial volume is 10 liter, and final volume V2 is 15 liter. Okay, so this is the given. Okay, so dq is given, v1 v2 is also given. Okay, so as we know from the first law, first law you all know, right? So first law is dq is equal to du plus dw, right? So that means dq is the change in heat inside a system. Du is the basically change in internal energy, and dw is the work done, right? And the sign of this work done will depend on that either the work done is done by the system, or the work will do on the system. Okay, depend on that, the sign of the dw will be decided. Okay, so now here, so as the gas expands, so we know as the gas expands here, so first there will be like change in the gas will definitely do some work. So dw, you know, p into dv. Okay, now here p is given, right? P is here given. I forgot to mention the p. So pressure p is 1 atm, right? So now so so this is given, everything is given. Now pressure is 1 atm. So pressure, so the work done will be 1 into v2 minus v1, right? This will be the change in volume. Okay, so now this is easy. Okay, so maybe 1 into v2, we know the v2, that is 15 minus 10. Okay, so that will give you 5. So work done is equal to pdv. So write it a bit clearly. So dw equal to pdv equal to this. So this will be become 5. Now we also have to conscious about the units, right? In the question itself, actually the units, the conversion unit is also given in the question. Okay, which is 1 liter dot atm equal to 0.1 kilojoule. Okay, so there is a reason, right, why this unit conversion is given here. So basically this thing is in liter and this thing is in atm. Okay, so the unit of this will be liter into atm. But we know all these things like dq itself is heat, that can be so that means basically it's a form of energy. So for dq also the units will be in joule or kilojoule, whatever. And for du also is change in internal energy. So but internal energy also, the like the units will be kilojoule or joule. So in that case we have to also convert our work done into kilojoule units, right? So for that reason this unit conversion here this unit conversion is given here. Okay, so now so so dw equal to 5 into 0.1 liter atm is 0.1 kilojoules, so that will become 0.1. So it will become like 5 into 0.1, so that means it will become 0.5 kilojoule. Okay, so this is the dw. Now so now you are supposed to find out the du, right? What is du? So du we can write from this first equation, du equal to dq minus dw, right? Now in the question dq is already given, the heat that is supplied into the system, right? So this is 2 kilojoule 2 kilojoule 2 kilojoule minus dw simply would be the work done, so that would be 0.5 kilojoule. So the change in internal energy will be uh, hello, hello, can you just hello? Okay, anyway, so good evening, Mahesh. So actually we are initially solving this last year assignment in thermodynamics. Okay, So we are starting from the first question. Okay, so uh, the question was like when uh, 2 kilojoule of energy is added to a 10 liter of an ideal gas, then the gas expand from 15 liter at a constant pressure of 1 atm, from 10 liter to 15 liter. Then we are asked to calculate the change in the internal energy. Okay, so in order to do that, first we write the information that is already given to us. Okay, so dq is given 2 kilojoule, right? The energy that is added to the system, that is 2 kilojoule. Initial volume is 10 liters and final volume is 15 liter. And against the pressure is like against the pressure we are doing the work, so that pressure is like 1 atm. And we simply use the from the first law of thermodynamics, we can write it like this, write it like this, right? dq equal to du plus dw. Dq basically is a change in internal change in the heat, du is change in internal energy, dw is the work done. Okay, so dw is already we have calculated, so that is the pressure into change in volume, v2 minus v1. So that gives like 5 liter per liter into atmosphere. And since we are calculating the energy, you have to convert the unit from liter in atmosphere to kilojoule, right? And in the question also, it's that's why in the question also it's already given 1 liter atmosphere is equal to 0.1 kilojoule. Okay, so we write it 5 into 0.1, that gives us 0.5 kilojoule. And from there so from there we calculate the du, that is 2 minus 0.5, that is 1.5 kilojoule. And so the answer of this problem would be change in internal energy, that would be 0.1.5 kilojoule. Okay, so that's how we done the first problem. Now we go to the second problem. Okay, so so the problem 2. Okay, so the problem 2 is 1 mole of an ideal gas expands from 10 atm against a constant pressure of 1 atm at 27 degrees centigrade. So this is given. Now we have to calculate the magnitude of work done by the gas. And here the information is given. The value of R is 2 calorie Kelvin inverse mole inverse, right? So basically 1 mole of an ideal gas expands from 10 atm against a constant pressure 1 atm at 27 degrees centigrade. So from here we have to calculate the work done by the gas. Okay, so so for that, so what we can do, so now the first we write the information that is given. Okay, so answer, so the information uh, for ideal gas. Okay, so the mole is 1 mole, so N will be 1 mole. And initial pressure P1 is given 10 atm and final pressure P2 is given 1 atm. temperature. So temperature is given 27 degrees centigrade. So I have to calculate the magnitude of the work done. Okay, so so now um, so now so this is the problem. So now the magnitude of the work done, and the gas constant is also given. So gas constant R is 2 calorie into Kelvin by mole. Okay, so now this is the given problem. Now now I have to calculate the work done, right? So what is the formula of work done? So work done basically is uh, minus, actually here the gas itself doing the work, right? So that's why there should be a negative sign involved here. If there is some work that is done on the gas, then it should be a positive sign, but here as the work is done by the gas, that's why we will consider in the negative sign. Okay, so now here the work done will be P external into delta V. So P external we know already, right? So P external is this. P external is this. So 1 atm, right? In the in the question itself, it's median against the constant pressure of 1 atm at 27 degrees centigrade. Okay. So this is already given. So now next thing we will be calculating delta V. So now delta V. Now delta V. So the question is, in the question only the volume, only the pressure is given. So basically what you have to do during basically in the during this whole change in pressure, the temperature is remain as constant. So what you can do, you can use the law of like Charles law, okay, or ideal gas law, whatever. So which basically says states that P1 V1 by T1 is equal to P2 V2 by T2. Okay, so here basically, so 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 basically V1 is, so T1 and T2 is equal, right? So we can write P1 V1 equal to P2 V2, right? So now we can write the so now now we write the main equation. We come back to our main equation, or delta V equal to V2 minus V1, right? So now we can write V2 as P V2 as P1 by P2 into V1, right? So minus P external will be V2 P1 by P2 minus V1 minus V1. Okay, so that's it. So now and so now we can just take P external V1 as common, and we know P1 value is 10 atm, P2 value is 1 atm. So we just substitute it here, 10 by 1 minus 1, and this will basically gives you P external is also, we know that is 1 atm here. From here we know that P external is also 1 atm, so we just substitute it here, and this is 1 atm, this is into V1, this is 10 minus 1, so this gives you 9 V1 liter dot atmosphere. Now here in the problem, so one second, so okay, so now, so in the problem actually we have to calculate the energy. So the thing is like here are like similar things, like we have to convert this liter atmosphere unit into the energy unit. Okay, so basically what we have to do, we know that 1 liter atmosphere is now actually in the problem itself, the whole thing, like the options are given in the calories. Okay, so previously we use the conversion from liter atmosphere to joule, but here we use the unit conversion from liter atmosphere to calorie. So 1 liter atmosphere is equal to 24.2 calories. So this information will be given in the problem. Okay, this conversion units. Okay, so now this thing is there. So now also we need the V1. How we calculate V1? So V1 calculation is pretty straightforward. Okay, so what you have to do? So we know the ideal gas equation, right? That is PV equal to nRT, right? nRT. Now initially when so we have to calculate the P1, right? So that means it would become at one point P1 V1 equal to nRT1, right? So now from here easily calculate. So okay, so can easily calculate the V1, right? V1 is equal to nRT1 by P1. Okay, so nRT1 by P1. So that basically gives us, so R value we already know. So 1 mole, in the question it's already given 1 mole, right? 1 mole into R, that is 2 calorie, 2 calorie Kelvin inverse mole inverse, so that is 2 basically. T1 is fixed throughout this entire process, so that would be simply 300, and P1 is P1 is 10, right? So P1 is 10, so that basically gives you 60 uh, 60 calorie per 18, right? Now just this is just put the V1 in the main expression, and okay, so now W will be equal to, now here it will be this thing, so it will be 60. So now in the problem it was given like so work done, so work done, we'll calculate the work done, right? So from this equation, from equation 1, so we'll to substitute this here. So from 1, so we just substitute here, so that will become W equal to minus 9 into 60 into 24.2. So if you basically calculate this thing, so that basically gives you, so that basically gives you 1 minus 13068 calorie. So this should be the answer. Okay, so this is it, a very like normal problem. Okay, so now like for ideal gas against a constant pressure, if it's expand, what would be the work done? So basically what we've done, we have written the initial pressure and final pressure, and this is the pressure against which the gas is doing the work, and the gas constant is given. But in order to calculate the work done, you also need the information of volume, right? So but in the problem itself, the volume information is not given. So because of that, we use this like Charles law, P1 V1 by T1 equal to P2 V2 by T2. So here, from here we can like P1 V1, that temperature is constant throughout this process, so we just cut this T, and so the we end up with P1 V1 equal to P2 V2. So from there we can write V2 in terms of V1, and that this expression is substituted here in this equation, and from there we calculate, just let me use a laser pointer, I think that will be easier. So from we like substitute this thing in this equation, then from there we will get this equation, right? And after that we substitute all the values, and we'll get this 9V1. Okay, now from here we all have to calculate the value of V1 also from here. So in order to do that, we use the ideal gas equation, P1 V1 equal to NR into T1, right? So from here we have calculated the value of V1. V1 is equal to NR T1 by P1, and NR T1 is already given. R is 2, T1 is 300, and N is 1, and P1 is 10. So from there we have calculated the value of V1 as 60. and after substituting all of this thing in this main equation, we get the work done, that is 13068, right? So this is the problem. Okay, I hope you understood. Okay, uh, so third problem. So let me just 1 second check whether the recording is happening okay or not. Okay, so recording is happening. Okay, okay, fine. So that's it. Okay, just it's fine. So so now let's solve the problem number 3. So problem number 3 is mm, so problem number 3 is which of the following statements is not true for an ideal gas. Okay, so now these are actually basically the statements. Okay, first statement is du dv at constant t equal to 0, b is du dp is at constant t equal to 0, option c is du dt at constant v will be equal to 0, and d is dh dp at constant t equal to 0. Okay, so which is not true, that means which statement is false. Okay, so u here is basically the internal energy here. Okay, u is the internal energy. Okay, so u is the internal energy and tvp is the temperature, v is the volume, and p is the pressure. Okay, so actually u first, u we know, u the expression of u, so we know the expression of u, there is no volume term involved. If you check in the expression of u, so there is no volume of term involved. So as there is no volume term involved in the expression of u, or in the expression of u, so for that case the first statement will never be true. Okay, du dv is equal to 0, so that statement is true actually. So we have to find out what is not true here. Okay, so this is true, so this option will be discarded. Then the second option is du. Similarly, there is no pressure term here in the expression of u, so here also t this is also 0, so this statement is also true. But the c statement, we know you know the expression of u, du equal to cp c dt. C means either it's constant pressure or constant, this is specific heat, c into dt. So dt term is there inside in the expression of du, right? So for that case, the derivative of u with respect to t will exist at a constant volume. So here the volume is constant, so that in that case it would be cv. Okay, so this thing should be non-zero, right? du dt at constant v, this thing should be non-zero. So for that case, this statement, that means, is not true, right? This statement is false, and we are like asked to find which statement is incorrect. So the option C will be the right answer. Okay, so this will be the right answer, which is not true. Okay, so this is a very simple problem. So like in order to solve this problem, basically you have to know the property of this internal energy, right? So These things also like helps you to solve like previous I mean next complex problems like if in if suppose in the system the pressure, volume, these variables are changing. Okay, so that will simply do not have any effect in the change of the internal energy. Okay, so this is an important like a concept, good to know actually. Okay, so the next problem is okay, so I hope you understood these things, this concept and all those things. Okay, so now okay, so now come the problem 4. Hmm. So the problem 4 is uh, let me write the problem. So this is all the things. So problem 4. Problem is the condition which holds true for an ideal gas undergoing free expansion under adiabatic process. There are three. There are. This is a MCQ problem, so there are multiple options. From that, you have to choose the correct one. So delta U is less than 0. Delta T is less than 0. Option B is delta U less than 0. Delta T greater than 0. Option C is delta U greater than 0. Delta T greater than 0. Option D is delta U equal to 0 and delta T equal to 0. So this is basically the problem. Now from here like now the condition which holds true for an ideal gas undergoing free expansion under adiabatic process. So which condition should be true? Okay. So now for this in order to solve this problem we need to know few concepts. Okay, so first thing first. So first thing is this is a ideal gas, right? So for an ideal gas, so what is free expansion? So in free expansion, basically in free expansion, a gas expands into a vacuum. Okay, that means there is no other agent is there, uh, without any external mm, without any external work being done or by the gas. So this basically is a high kind of hypothetical concept. So here what actually it states that during the free expansion the gas, the ideal gas, is expands in a vacuum. So vacuum means there is no other external agent is there, so basically nothing is there in that system to like resist that free expansion or to enhance the free expansion. So So as there is no external agent, so basically during this expansion the gas will not do any kind of work. If there is some external agent is there, like some another gas or some piston or something like that, so when the gas expands, it basically has to do some work against that external agent, right? But for this system, as it's doing in the vacuum and the gas like expands, so basically it doesn't do any kind of work. So but that thing, so work done will be 0 for free expansion. Okay, dw equal to 0. Okay, now next is called adiabatic process, right? So this in the question it's given adiabatic process. So what is adiabatic process? Let me write this also. Adiabatic process. So and so during this process, no heat is exchanged between the system. That means in our case it will be the gas, so that means the gas and the surroundings. So this is basically the definition of a adiabatic process. So basically this means that during this adiabatic process, the change in heat between this gas and the surroundings will be 0. So that means for this case for this system, as it's a adiabatic system, so here dq will be equal to 0, right? dq will be equal to 0. Okay, fine. So this information is already given now. So now we are supposed to find uh, which of this from these 4 conditions are true. Okay, so now we know the from the first law that so all one thing is there like dq. So anyway, so now dq equal to du plus dw, right? Now in this problem du can write dq minus dw. Now both this dq is 0, dw is also 0, so that means du is also 0. Okay, and do you know du is here like c into dt. C is a specific heat, so that is also 0. So similar dt is also 0. That means because this specific heat, this is a specific heat. So for gas this specific heat cannot be equal to 0, right? This cannot be equal to 0. So the only solution would be dt equal to 0. So that means the option D will be correct. So right. So option D would be the correct answer. So where dt will be equal to also 0 and D will be also 0. So fine. So this is the answer for this problem. Okay. So now let me shift to problem number. Okay, so let me shift to the problem number 5. So this is the 4th problem. Now comes the 5th problem. Okay. So let me see the chart. So now the 5th problem is there. So so the 5th problem, what is asked that uh, 1 mole of an ideal gas Cv is the given for this ideal gas, that is 2.5 R is allowed to expand at 300 Kelvin from 10 atm to 5 atm. Okay, so this is given against an opposing pressure of 1 atm. Okay, so what you have to find out after the expansion, the gas is heated at constant volume until the pressure becomes 10 atm. Okay, and you are supposed to find out the change in internal energy. So okay, this is a very big problem, so let me also write options that are given. One is minus 249.42. All this is in joule. Okay, this is all joule. A, B is the option 648.4.92 joule. C is 0 joule, and D is 6235.5 joule. Okay, so this is the problem that is given here. So now so 1 mole of hydrogen is allowed to expand from 300 Kelvin from 10 atm is the opposite pressure wanted after the expansion of the gas. So first here is two processes happening here, right? So first process is like against the process one. Let me write this. So process one is CV. So the first the gas expands. During the expansion the temperature remains constant but the pressure is changing, so that means volume is also changing. Okay, so during the process one gas expands from 10 atm to 5 atm at 300 Kelvin. Okay, and so this is the process first, and against the P external pressure that is equal to 1 atm. Okay, so during the first process the gas expands from 10 atm to 5 atm, and how do you calculate that? So so for this first process, as like there is like no heat is coming. Okay, so basically that means from the first equation du equal to dq plus dw, right? So here what is happening, so as there is no change in heat in the system, so dq part will be 0 completely, so du simply will be the dw. Now here the dw is gas expands, that means volume will be changed, so dW will be P external into dV. So in terms in delta form, P external into V2 minus V1. Now here, like we have done a similar problem, similar type of problem, like earlier also, where like when the gas expands, the things that are changing is given is pressure, not the volume, right? So here also the same case. Uh, that here also like the change in pressure is given, not the volume. So but we can the previous we can also calculate the change volume, right, at that pressure, right? So for that we will use the similar with the ideal gas equation. Okay, that is PV equal to nRT, right? So PV equal to nRT. Okay, so the for so let's calculate for first calculate V1. V1 is equal to simply nRT1 by P1. So nr value you already know, n is like n is 1 mole given, right? 1 into r value you all know, that is the ideal gas constant, that is that 8.314, 8.314. And that is in joule. Okay, and T1 is also given. Okay, T1 is what is the T1? T1 is 300, right? 300 by P1. P1 is from 10 to 15. That means P1 should be 10, right? Expand from 10 atm to 5 atm. P1 should be then 10. One thing I missed here. So here basically the gas, the work is done by the gas. Okay, so that means there should be negative sign also. That dW is minus of this thing. Here also I've written it wrong. So it should be dq equal to du plus dw, right? I have sorry. So basically I have written the wrong way. So du in this case will be dq minus dw. Okay, so dq here will be 0. Okay. Okay, so previously I have like done a mistake. So this is the actual law. So here dq equal to dq minus dw, at dq is 0. So dw are calculating. So that is v1 we have already calculated. Now we will calculate the v2. That is nRT2 by p2. Similar way you just calculate. Okay, 1 into 8.314 into 300 by 5. P2 is 5. Here to just substitute here delta W. P external, you like everything, like you have to change the units and all. Okay. So if you do all of this thing and and do the calculation, you will get delta W equal to minus 249.42 joule. I'm not doing the calculation. Okay, just you do it yourself. So just be conscious about the units that you are taking during the during solving this equation. So this will be the delta W. So now from this what we can do, no, so you get the delta W. So delta W we already have stated here. So du equal to minus dw. So that means delta U will be minus of this 249.42 joule. So basically this gives you 249.42 joule. So minus minus will become plus. So this will be delta U. Now this is, remember, this is the process 1 that is happening, right? Not so now next we come to the process 2. So process 2. So during this process to the after the, so this is written here. So process, this is the process. So after the expansion, the gas is heated at constant volume until the pressure becomes 10 atm. So in that case, so initially we remember the gas is shifted from 10 atm to 5 atm. So now right now it's on 5 atm. Now During the second process, the gas is kept at a constant volume. That means volume remain constant, and in this case pressure is again changing, and also we are supplying heat into the system. So as V remains constant, the variable or the coordinates that are changing is, one will be the T and second one will be the P. Okay, so let me write it. So here what is happening, process 2, the gas expands. So after the gas expand, the so the gas heated in constant volume, right? So dV will be 0 in this case, so work done will be simply 0, right? And the pressure changes here. Pressure changes from 5 atm to 10 atm. Okay, so this is the change in pressure. So as volume is, so we know P1 V1 by T1 is equal to P2 V2 by T2. So that means volume is remain constant, so V1 equal to V2, that is remained as constant. So P1 by T1 is P2 by T2, right? And we already know P1 and P2, right? P1 is 5, T1 is 300, right? Because first process the heat was 300 Kelvin, and that is actually remain at a constant during the first process. So T1 will be the 300 Kelvin. P2 here is 10, because it's like pressure changes from 5 to 10, and T2 have to calculate. So it's pretty much easy how to calculate it from here. So here basically T2 will be 10 into 300, basically gives you 600 Kelvin. So as you can see, so here pressure is changing, P1 that is 1 atm to P2, sorry, 5 atm P1 to 10 atm P2. So T1 is also changing from 300 Kelvin to T2, that is 600 Kelvin. Okay. So volume is remain as it is. Okay. Now during this process, as you know, T is changing. That's a significant thing. So in the so we know that, we already know that delta U is equal to N CV dt. And this, in this problem also you can see this, because they know that we need this information, so that's why CV value is already given here. Okay. Now if we have to just substitute, so let me change the word, d delta U equal to 1 into the CV here basically is the 2.5 R 2.5 R, and dt is the change in temperature, that is 300 to 600. So so if you just calculate this so so if you calculate this, so this will give you delta U equal to 6235.5 joule. So that is, let's term is delta U2, because this is the change in internal energy during the process 2. So for that, let characterize this variable as delta U2. Okay. Similarly, let us use here delta U1. So now the total change you can easily calculate. Okay, that would be delta U total, right? Delta U total would be delta U1 plus delta U2. That means that would be equal to, first we have calculated, that is 249, that you can approximate as 249.42. So 249 0.42 plus 6235.5 joule. So if you add this will give you 6284.92 joule. So that would be simply the answer of this answer, option B. Okay. So let me revise the whole thing that we have done. So in the problem, what is given, 1 mole of an ideal gas is allowed to expand. Let me use the laser pointer. So 1 mole of an ideal gas is allowed to expand from 300 Kelvin from 10 atm to 5 atm. Okay, this is the first process. So during this process, as there is expansion is mentioned here, but since the volume change is not given, so we just use pressure and temperature, all the things are given. So we can easily calculate this using the ideal gas, right? that we have done here. So as you can see, use the ideal gas equation to calculate the V1. Similarly, at the like final pressure, that is at 5 atm, similarly we have calculated the V2. And during this process, now so V1 V2 we got, so change in volume also we can calculate. And during this process, as there is no dq changes mentioned here, so dq have made 0 in the first law of thermodynamics. So from there we can get d equal to minus dw. Okay, now here the work done is by the gas, so in that case we consider the negative sign here. And next thing is that now p the work done, we know p into dv, so p external into v2 minus v1. So v2 is this, v1 is this, just simply substitute it here, and if you calculate you will get this dw, that is minus 249.42 joule. This is negative, and if you substitute this here, so negative will become positive, so that will give you 249.42 joule. So that is the change in internal energy during the first process. Now for the second process, what is happening, after the expansion the gas is heated at a constant volume until the pressure becomes 10 atm. So similar for process 2, the gas is heated at constant volume. Okay, so dV during this entire process, the volume change will be 0, so dV will become 0. And pressure is changing here, so pressure changes from 5 atm to 10 atm. Okay, so now here so pressure is changing but the volume is remain constant, so that means temperature is also changing. That we can assure from this gas equation here, from charge equation here also you can see P1 V1 by T1 equal to P2 V2 by T2. V1 V2 is constant, so here, so this is the relation we'll be getting. From this relation it is quite clear that as P1 P2 is changing, similarly T1 T2 will be changing. So we have the value of T1 at 300 Kelvin given in the problem, and from there we can easily calculate the T2 here. So that's it. So we have calculated the T2, that gives 600 Kelvin. So now here the part is like you have to calculate the change in internal energy here. So basically change in internal energy delta U, we know the change in internal energy depends on change in the temperature, right? Delta U2 simply is the NCV. CB we are using because this whole things is happening under constant volume, right? So that's why I'm considering CV only here. So CV is there, and dt is T2 minus T1. So that is 600 minus 300, so that gives us 300, and CV is 2.5 R. So if we multiply these two things, so which will gives us 6235.5 joule. Okay, fine. So that gives us the delta U2. Okay. So one more important thing. So if you like meeting is again like stop or something happens, so in the comment box I've mentioned like a backup link. Okay, in the comment box you can see in the comment box it's already there. Okay, so if the meeting like stops or something happen, you can join by this backup link. Okay, in case, I hope that is not happening, that will not happen. Okay, but if it's like happened, then you can join join the meeting using this backup link. Okay. it's just save it in your computer. Okay, because if it suddenly stops, then this will be helpful. Okay, So this is up to mention. So that's it. So this is the questions of the class. Let me just also check whether the recording is happening well or not. Hmm. Hello, hello. Okay, so everything is recording is happening. Okay, okay. Okay, fine. Okay, so if you have any kind of question, you can ask. Okay. So otherwise, you can simply go to the next problem then. So I hope there is no problem. So in that case, I'll move to the next problem then. Okay. It is the problem number 6. So problem number 6. This is a very short problem. Okay. So the exact differential is what? There are 3, 4 options given. Here is del Q reversible, B del Q reversible by T, C is del Q irreversible, RIREV, and D is del Q irreversible by T. So before solving the problem, let me first discuss about what is actually exact differential equation means. Okay. Like when I mean these are basically equations, right? So which characteristics of a equation like confirm that it's a exact differential or not? Okay, so how can you characterize the exact differential form? It's in an exact differential form or not? Okay, so to do that, so so let's take a equation. Okay, so this is a equation. Let's suppose pxy into dx plus qxy into dy equal to 0. Now, although this concept is not needed for the in order to solve this problem, but still this needs to like you should know how this how to know whether the equation is exact differential or not. So this pxy and qxy both are the function of x and y. Okay. So if suppose del p, if you do the derivative del p del y is equal to del p of del x, in that case, if this condition is satisfied by p and q in this equation, then this equation is a exact differential equation. Okay. So that means that you can basically write this equation in this form. Okay, like the solution of this equation like in this form: d of some like phi as 0, then the phi will become C. So this basically will be the solution. If you do the integration, let's suppose I do the integration 1 to 2. Okay, so solution will be phi 1 minus phi 2. As you can see, this the main thing of this thing is that the solution only depend the initial value of phi. Sorry, this should be phi 2 to phi 1. Okay, so initial this. Okay, that's fine. Okay. So initial value of phi 1 and final value of phi 2. Like between that, like what is the path taken by phi, that is not important here. Okay, if a equation is exactly differentiable. Okay, so like the phi value is only dependent on the initial and final value. Like how it reaches from initial to final value, that is not important here. Okay, so so similar way in this problem also, what is given in this problem also similar thing is given. It's like delta q reversible. So in thermodynamics, just first state some things. So in thermodynamics also there are some things that is called path dependent function, and some functions are not path dependent. Okay, so right, so there are two types of thermodynamic functions. One is path dependent, one is path independent, right? So this basically means for path dependent function is that how, let's suppose state A to state B. So for path dependent function, which path you are using from reaching from state A to B. Let's suppose one take this path, one take this path, one take this path. So the values of path dependent function for this process, I mean going state A to state B, will be different, like for 1 2 3. Now the for path dependent function during this process 1 2 3, the for path dependent function the values will be different. Okay, because it is dependent in path. So although you are going like from A to B in both these three processes, but still the paths are different here. So you will get different values of thermodynamic functions, path dependent thermodynamic functions. But for uh, change in like the function, change in the path dependent thermodynamic functions. But let's suppose for path independent function, only only it matters is the initial and final value, whichever path you can take in, like for 1 2 3, but whatever path you take, the for path independent function, the path independent function basically doesn't change from state A to state B. I mean doesn't change, me doesn't depends on the change, how the path is changing. Okay, it only takes, let's suppose phi is a path independent function. So phi, the change in phi from process A to B, let's say d phi or delta phi, that is only depend on phi B minus phi A. Okay, but so that means this phi is exact differentiable. Okay, so path independent functions are basically exact differentiable. Okay. So now here let comes into the problem. So in the problem, there are many options are there. Okay, so as we know, this is for ideal gas. So ideal gas we know, and let me just gives you some example of path dependent function. So path dependent function basically dq, change in temperature, change in heat dq, or change in what is that called, work dw. So these are all path dependent. For path independent functions like change in internal energy, this is path independent. Similarly, change in entropy, this is also path independent. Okay, so entropy, properties like entropy, entropy or internal energy, okay, during a process from A to B, this change in internal energy and entropy will only depends on the initial and final value. Okay, but if you consider work done or a temperature or work done or a change in heat, so that is not only dependent on the initial final, that is also dependent on the path that you are taking during the process. Now here the interesting thing is, so here what is happening, so here we know uh, dq reversible basically is t into ds. Okay, this is only true for reversible process. Okay, for irreversible process this is not true. So for reversible process we can write sorry, dq reversible equal to t into ds. So ds equal to basically dq reversible by t, and we know this is the property of ds, that this is a path independent function. So that means we can write ds as an exact differential equation which only depends on the final and initial and final state. Okay, so this is ds is initial is, so that means that ds basically, so basically you can write the, we can write we can write dq reversible by t as ds, and the ds is as path independent function. So this can be a this should be exact differential equation, exact differential form. Okay, so the right answer will be the option D. Okay, q reversible by t. Okay, so this is question 6. So if you have any doubt you can ask, like I can like then give so much for example, like how this exactness is related with the exactness of differentiability is related with the path dependence. Okay, anyway, if you have any question you can also ask. So this is the question number 6, we have done it. Now we go to the, let's see if we check. So this is now question number 7. Question number 7 is a bit interesting one. So state whether the following statement is true or false. Okay, so the statement is here. So changing internal is the heat exchange that takes place in constant volume. So this is the statement that is mentioned. So the change in internal energy of the change in internal energy is the heat exchange that takes place in constant volume. So uh, so that statement, like you have to show the whether this is a true statement or it's a false statement. Okay, so this is very like not a very difficult problem. So we know that, right, from first law, from first law of thermodynamics. Du, let me try it in delta format. Del- Delta U, delta W. Now delta W we all know, right? Delta W is equal to, this is basically the work done, right? This is the work done. So work done will be P into dV. P into, write it as delta V. So now what happens, here it's mentioned that this whole process is happening at a constant volume. So that means dV will remain at 0, right? So that means delta W will remain at 0, right? So now delta Q is delta U and this is 0. So the question is, a change in internal energy is the heat exchange that takes place at constant volume. So this is the change in internal energy, change in internal energy, and this is the change in heat exchange. Okay, so and this whole thing is in constant volume. So that means this statement is true, right? True. Okay. So this is very straightforward, like from the first law of thermodynamics, you can easily prove these things. Okay. So now comes the. So if you have any kind of doubt, you can ask me. Okay. Okay. Finally, this is the seventh problem. Here also you can do the problem number 8. Okay. Okay. Similar type of problem also. Similar type of problem also given here also. Okay, so write the problem. So similarly, like here, whether whether the following statement is true or false. And the statement is this statement B, actually previous problem statement was in. So if a perfect gas expands against 0 external pressure under adiabatic conditions, then its temperature fails. So this is the statement that is given. Now your work is like you have to show whether this statement is true or false. Okay. Now in adiabatic, so this is the adiabatic process, right? Adiabatic process. So I've already discussed the basic theory, the basic assumptions that you have to take when the process is adiabatic, and that is you have to take uh, dq equal to 0 because there should be no heat exchange. So that is one of the property of adiabatic process. So dq will be equal to 0, and no heat exchange between the system and the surroundings, and it's like external pressure will be 0. So now now the if the perfect gas expanding is 0, so work done, if you consider the work done is dw, that mainly p external into dv. Although the dv, like there is change in volume, right, but since the external pressure is 0, so this process, I think you remember what is the name of this process, right? This process is basically the free expansion, right? Where like in the system, where like in the surroundings there are nothing, there is vacuum in the surroundings. Okay, so when the system expands or contract, whatever happen, the system will do or no work, or there will be no work that is implemented on the system also. That is called free expansion, and we know that during the free expansion the work done will be 0 because p external is 0. There's no nothing, no pressure, nothing is there against which it will do some work. So work done will be again equal to 0. So from the first law again, like from the first law of thermodynamics, we know dq equal to du plus dw, right? Now for this problem, dw anyway is equal to 0, dq is also equal to 0, so du is also equal to 0, and du is, we know, cv into dt. So cv cannot be equal to 0 because this is a specific heat of a gas cannot be equal to 0. cv not equal to 0, never be not equal to 0. So the only solution is dt will be equal to 0. That means there is no, like, there is no change in temperature visible. dt is 0, then that means a change in temperature. So dt will be equal to 0, so which basically suggests that no change in temperature. So now comes to the problem. So here the question was, if a perfect gas expands against a 0 external pressure under adiabatic condition, its temperature fails. We can see there is no change in the temperature, so that means temperature not fails, right? The temperature remains constant. Okay, so that means this statement is false, right? Okay. Okay, so this is it. The dt will be equal to 0, and simply there will be no change in the temperature, so the temperature doesn't fail. So this is the question number 8. Now we'll go to the question number 9. Okay. For question number 9, for an adiabatic reversible expansion of an ideal gas the plot of log P versus log V is linear with slope equal to, the options are given. In option A it's 1 by gamma, option B is minus 1 by gamma, option C is normal gamma, D is minus gamma. Okay, so these are the options. So just think about, so I guess you know this is a adiabatic reversible expansion. So the ideal gas equation for an adiabatic process is we can use a different equation, right? For a adiabatic process, I mean there is a different relationship between PV that equally holds for an ideal gas which is gone through under a adiabatic reversible process, right? And that relation is this, right? P into V gamma equal to constant, right? That P is the pressure, what do you all know, pressure, V is the volume and gamma is a very important thing. This is basically the ratio of specific heat at constant P and specific heat at constant V. So gamma will be simply Cp by Cv. Okay. So this I assume that this relations, how this relations comes and all of this thing, you know, like in the classes I think these things have been taught well. Okay. So I'm not doing the derivation. So this is already given. Okay. Now from this equation, so let me just once again write this equation. So P into V into gamma is equal to constant. But in the problem, you are not asked to find the relation between P and V, right? You are asked to find the relation between log P and log V, right? So how do you, so this is very straightforward. So what you have to do, just take the log on both sides. Okay, so log P into V gamma equal to log constant. So this gives you log P plus gamma into log V. Okay, this will be equal to 0 because constant, I mean log, if you take log on any constant, this simply gives you 0, right? So this gives you 0. So now then log P equal to minus of gamma into log V, right? Now now this is this so this is it. So this you can write it as K, okay, plus K, something like that. Okay, so this is it. So this k basically is a constant. It can be 0 also. If this is 1, then it's from 0. So this k is constant here. So this basically you can identify this equation, right? If you take here, if you remember here what's given here, it asks that you have to find the curve between log p and log b. Okay, not p and b, log p and log b. So so you can take log p as x minus gamma and log b as y plus some constant k. So this basically gives you the same equation like straight line equation. X equal to mx my plus c, or y equal to mx plus c, anyway. Okay. So this will be the equation. So here m, what is m? M basically gives you the slope, right, in this linear equation. So here what is the slope? Here slope is minus gamma, right? Okay. So this is basically the equation. Okay. So uh so let me check what are the answers that are given. So these are the answers given. So you understand, right? So here what is the correct answer? The answer is minus t, right? So this would be the correct answer. Fine. Okay. Then comes to the, this is the problem number 9. Now comes the problem number 10. So let me write the next problem. In ideal gas in a cylinder, diabatically compressed diabatically to 1/3 of its initial volume. Okay. During the process, 20 joule work done on the gas, right? This is important. On the gas, not by the gas. On the gas by compressing agent. Compressing agent. Then you have to find out which is true. Okay. So first option is change in the internal energy in the process is 0. Option B is the internal energy increases by 20 joule. Option C was internal energy decreases decreases by 20 joule, and option D is the temperature of the gas decreases. The temperature of the gas decreases. So these are the four options that are given in the problem. So, okay. So what are the things? Okay. The first thing is this is the adiabatic process, right? Answer. So first thing is that this is a adiabatic process, right? So adiabatic process means what? That means adiabatic process means dq will be equal to 0. So basically there is no heat exchange in the system, so dq will be equal to 0. Now uh, now it's mentioned that here if you see it's mentioned that during the process 20 joule work done on the gas by the compressing unit, which is true. So uh, there is some external agent is there which is basically doing some work by compressing the gas, and as the work is done on the gas, so for that case we can consider dW as plus 20 joule, right? Because uh, it's done by the gas or on the gas? Done on the gas, right? It's gas done on the gas by the agent, done on the gas. So that means the dW is negative. So dW is 20 joule. So now on the gas, so that means it should be negative. Sorry. So no, so on the gas, that means this dW should be negative. So 20 joule. Sorry, my apologies. So this is done on the gas. On the gas, when it's on the gas, that should be negative. So dW will be minus 20 joule. Now, let me write as done on the gas, right? That should be negative. So now from the first law of thermodynamics, we know dq equal to du minus plus dw, and we are supposed to ask the internal energy. So the internal energy change, dq is 0 anyway because it's a adiabatic process, so d equal to minus dw and minus of minus 20 joules, so that means plus 20 joules. So that means the change of internal energy, the internal energy basically increases. Change in internal energy is positive, that means its internal energy increases, right? So now check the options. So increases, so this option B will be the correct answer, right? But the internal energy increases by 20 joule. Okay, so that's it. It's fine. This is the problem number 10. Okay, now comes to the problem 11. You can problem number 11. So what is the problem number 11? Check everything is happening correctly or not. Recording is happening okay. Fine. So the problem number 11. So just given, so basically in a cyclic process, four options are given. You have to select one of them which should be true. Option one is work done is 0. Option B is work done by the system is equal to the one equal to the quantity of heat given to the system. Option C is work done does not depends on the quantity of heat given to the system, and option D is the internal energy of the system increases. Okay, so these are the all the options are given. Now you have to find out that in a cyclic process, out of these four given options, which should be the correct options. Okay, so for that, what we will do now, so first thing is that what is a cyclic process, that you have to first understood, right? So cyclic process, so cyclic process, so what is a cyclic process? So cyclic process is like that system is A from B, so system is going from A to B, then again comes to B to A. So it's like wherever the system starts, it basically ends up with that state. So here the system starts at state A and it goes to start B, and then it again return back to state A. So which this whole thing is a cyclic process. So basically the process like ends up in the same state where it starts with. Okay. So now we have already talked about time dependent and time independent functions, right? So sorry, path dependent and path independent thermodynamic functions, right? Now here you can see the initial and final states are equal. Okay, right? So that means for if the state is not path if the state is path independent, in that case, I mean the functions that are path independent, for those function for this kind of process, the change of those function for this kind of process will be equal to 0, right? And one of the functions is path independent function is U, internal energy, right? Is path independent function, right? It only like depends on the starting and ending point. So here delta U, that means will be equal to 0 for a cyclic process, right? Similarly, like here if you substitute it in the first, like we know the first law. Okay, so let me begin from the first law. From the first law, T equal to dq plus dw, right? So du is anyway equal to 0. So what, sorry, I written it wrong. This should be dq equal to du plus dw. Okay. So here du will be equal to 0 because in change in internal energy basically 0 here for path independent function. So basically dq will be become dw here, right? So what does that mean? That means that the change in the heat will be simply equal to the work done. So that will be the option B, right? Work done of the system is equal to the quantity of heat given to the system, right? So option B will be the correct option here. Okay, fine. If you have any doubts regarding this problem, you can ask. Okay. Otherwise, I'll shift to the next problem. Okay, then the big problem. So problem number 12. So 1 mole of ideal gas with CV equal to 3.0 Kelvin inverse, mole inverse, initially at STP is put through the following reversible cycle, right? So the cycle is given like this. So during this first state 1 to state 2, heated at constant volume to twice temperature. So this is the first process. During the second process, state into state 3, here what happened? Expands adiabatically back to its initial temperature. Okay, then 3 state 3 to state 4, no, state 1. This is basically reversal, so this is goes back to state 1 actually. So okay, state 4, sorry, should be state 4. Compressed isothermally back to state 1. Now 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 during this whole process you have to calculate the delta U in calorie. for the cycle. Okay. Hmm. So many things are given actually. So CV is given, initial state it's mentioned that it's in STP, right? STP means standard temperature pressure. That means temperature should be in 273, uh, and pressure would be 1 atm, right? And first, like, temperature will be twice, so T2 will be 2 into T1. Then it expands adiabatically back to its initial temperature. That means uh, from 2 into T1, it again transforms to T1, and at last it compresses isothermally back to state 1. That means the during this whole process the pressure is also changing, right? So so the change in pressure, like, we have to also account that also. Okay, so let's do it. So there is a very like simple also you can solve this problem, but I'll come to it later. I'll tell that way little later. Okay, so first thing is that temperature is changing, right? So during the process 1, T1 goes to 2T2, 2T1, right? T1 goes to 2 into T1 as the temperature is changing. So it's basically state that twice of the temperature. So delta U for this case will be NCV to T1 minus T1. So NCV into T1. That would be delta U1 for the first case. Okay. Uh, that is the first case. For the second case, what is happening? The gas expands adiabatically back to its initial temperature. So what actually happens here? So so basically what is happening adiabatically? So dq here is 0, that is adiabatically, so no dq is involved to back to its initial. So similar thing, delta u equal to minus ncv to t1 minus 2t1, because initially it's t1 and comes to t1. So initially it was 2t1, then it comes to t1, so minus n cv into t1. Okay, and third is the what is said that compress isothermally back to its initial state 1. This process is happening isothermally, right? So temperature is not changing here, so delta u simply will be equal to 0. So delta u total, delta u1, delta u2, delta u3, delta u total will be delta u1 plus delta u2 plus delta u3. This is basically NCV T1 minus NCV T1 plus 0. So that will give us here. Now the funny part is, like, I have calculate this delta U total by calculating the change in internal energy during all these three processes, and from after calculating all of this delta U1, delta U2, delta U3, I can tell this is a I mean change in overall delta will be 0. But I can also tell it from, like, from the first place also. Like, you can see the state starts from 1, then it goes to 2, then from 2 to it goes to 3, and then again from 3 it comes back to state 1. So what does that mean? That means 1 2 3, 1 to 2, 2 to 3, 3 to 1, which means it's a cyclic process, right? And we know, for cyclic process, the thermodynamic functions, like this internal energy, which is a path independent function, which is simply will be equal to 0, right? Delta U will simply will be equal to 0 for this kind of cyclic processes, right? So from that also we can just, from the problem itself, we can easily like conclude that this, during this whole tree process the total change in the internal energy will be equal to 0. So that is also can be done, but just to assure you that in like in reality also it's happened like that. So that's why I done the entire calculation. So but from the problem itself also it's quite sure that it's I mean it's a cyclic process, and the total internal energy will be changing, the total internal energy will be 0. Okay, so now the last problem. Okay, so this should be the last problem for this session. So problem number 13. So problem number 13 is very like kind of a okay, so so uh, it's like one one mole of ideal monoatomic gas is allowed to expand isothermally at 300 Kelvin from 1 atm to 0.1 atm. Now if it's a reversible process, what will be the change? What is delta G in kilojoule? Delta G basically nothing but the Gibbs function. So I hope you know the, I don't know, delta G is like anyway I just tells you. So what happened? So let me just gives you the expression of the delta G. Okay, so in next problem answer session I maybe will discuss more about this Gibbs function delta G, but for the time being I just write the expression of delta G. So for an isothermal process, the delta G will be minus, minus T into delta S. Just for the sake of this problem, just to use this expression, but in the next problem answer section where we'll go more deeper into thermodynamic function like Gibbs function, Helmholtz function, enthalpy, all those things. Then we'll discuss in more detail about this Gibbs function. Okay, so for right now, this is this we are actually using. So delta G, T delta S. So we first have to calculate the delta S, right? So delta S is uh, now we know that for isothermal expansion. Okay. Mm, isothermal expansion. So isothermal means T should be remains constant, right? So ds will be nr ln v2 by v1. This is the change in entropy. Change in entropy during isothermal process. Okay. Now now v2 v1 we can easily calculate p1 v from Charles you can p1 v1 is p2 v2, because in the problem is given in terms of pressure. So p1 v1 is p2, so b2 by v1 is simply P1 by P2. So if you calculate ds in R P1 by P2, so ln was there, so ln nr ln P1 is 1 atm, P2 is 0.1 atm. So this basically gives you n is also 1 mole, so 8.314 into ln 10. That basically gives you 19.14 joule per Kelvin. This is the delta S change in entropy. Now from here T is already given, right? T is the 300 Kelvin. So from here the delta G is easy, right? Delta G is T into delta S. So 300 into 19.14, that basically gives you 5.74 kilojoule. So this will be the change in delta G. Okay, so this is our last problem. So I hope all of you guys have understood this whole thing. So if you have any kind of doubt, you can ask me always. Okay, so if you have any doubt, you can ask. Anyway, if you don't have any problem, then I can just stop the recording.